Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. This is the last lecture of the whole series. This is lecture number 60 and we will start from where we left in the previous lecture, which is lecture number 59, and we will continue our journey for looking into the various 2D materials which are available. So we will look into the 2D materials and look into van der Waals materials. For example, another example of that is graphene 2D material, which we have already discussed in, if not in great detail, at least the precursor to it in the previous lecture. Then classification of 2D materials. We will look into 2D families of material and how is it different. Okay, so let's go for the first of all to the van der Waals material. As I told you, what are the van der Waals materials basically? These are layer by layer material, right? So they are actually peeled up in layer by layer, and these two layers, two subsequent layers. So I have one layer, let us suppose, is formed here, and then there is another layer which is formed, let us suppose, right, like this, and they are just connected with each other through weak forces, right, weak forces here. And these individual layers are actually held together by weak forces, as I discussed with you, and this force is basically known as a van der Waals force. And therefore, the in plane bonds are much more stronger as compared to the orthogonal bonds, which are basically a pz orbitals which are there. Typically the monolayer thickness is of the order of 0.35 to approximately 0.65 nanometers. That is the range of monolayer thickness which you see. And obviously, as I told to you, this 2D materials will have a property which is very unique and different from bulk materials. However, the van der Waals forces are electrostatic forces which arise from dipole induced dipole or a dipole dipole interaction. So it's basically there are two dipoles in nature, and let's say I have a dipole which has got a positive and a negative pole available with us, and if there is a weak force which is available very close to each other, then there is a weak sort of electrostatic force between the two, and this is known as a dipole induced or dipole dipole interaction. So these basically van der Waals forces arise from that dipole dipole interaction in a sense. Now what are dipole? Obviously those materials which or the class of materials where individual layers are held together by weak van der Waals forces, they are basically known as van der Waals materials. And now since they are in layer by layer and sheets, exfoliation is relatively easier in this case as compared to any covalently held intersheet material. Now these materials have unique properties due to their layer structure, and since the interlayer interaction is very weak, typically they are, though mechanically unstable, because in the sense that they are layered over one another, but they do have good electrical properties beyond a point. One of the dispersion forces is also referred to as a London force, which arises because of temporary fluctuations in the electron cloud. So you have electron clouds available where the density function of the electrons becomes very large, and they create instantaneous dipoles, and then they get destroyed over a period of time because of fluctuations. These fluctuations come up because of mechanical in nature or temporal in nature. Also they give rise to because of fluctuations at instantaneous points. So this is the reason you get these dispersion forces available to us. When we come to dipole dipole interactions, and they occur between molecules with permanent dipoles. So if you have two molecules with effective permanent dipoles, of opposite nature of the dipole will attract with each other, and they are much stronger as compared to ordinary dispersion forces, but they are weaker than covalent or ionic bonds. So they are somewhere between the dispersion force and the covalent bonding. If we look at the dipole induced dipole forces, so typically this occurs in those regions where you have polar molecules, right, and polar molecule induces a dipole in the neighboring nonpolar molecule. So because of its relative proximity to the nonpolar molecule, they tend to polarize it beyond a point and form a dipole induced dipole force. uh, Most of you are aware of hydrogen bonding. This is a strong dipole-dipole interaction involving hydrogen bonded to highly electronegative atoms, for example, nitrogen, oxygen, and fluorine. So, this is typically the hydrogen bonding which you see. So, these are the various types of interactions, physical interactions which happen: dipole-dipole interaction, dipole-induced dipole forces, and hydrogen bonding. Now, let us look at the graphene as a 2D material. If you look carefully, then typically the advantage, as you can see here, is its mobility, which is very high, of the order of 15,000 centimeters square plus volt second, and they are generally used in quantum Hall effect. Now, if you look at its sort of conductivity here, which is 1 upon resistivity, then typically at 10 Kelvin, if you look, it has got a very low conductivity as the temperature, as the changes there between the van der Waals forces. There is always a sudden change in the value of sigma. This is basically my longitudinal resistance which you find out, rho xx, and this is sigma xy is the Hall conductivity which you find out, given as 4 e square by h as its sort of dimensions. Then typically what we find out is that for higher values of n, which is basically number of particles per centimeter square, the sigma value goes on increasing. However, there are local areas where you will see that the rho xx value becomes constant at certain value and then suddenly rises. So, this is basically to do with the confinement of the electrons in the 2D materials. Now, let us look at the classification of 2D material. There is a superconductors 2D material, semiconductor 2D material. So, what is semiconductor 2D material? Is a material with electrical conductivity that obviously lies between the conductor and the insulator. And examples are MOS2, which is molybdenum disulfide. We have WS2, which is tungsten disulfide. We have WSE2, which is tungsten diselenide. We have ReSe2, when we write, it is rhenium diselenide, and TiAC2, which is titanium diselenide. What is a superconductor? Superconductor, obviously, as you all know, that exhibits zero electrical resistance below a critical temperature, known as the critical temperature, and they have the ability therefore to expel the magnetic field out of it, right? And this is also referred to as a Meissner effect. And examples are niobium diselenide, niobium disulfide, titanium disulfide, and iron telluride selenium, right? These are the few examples of superconducting 2D material. But as far as electronics are concerned, we are more interested with the top part, where MOS2 has come up in a big way for all practical purposes. So, molybdenum disulfide, this and WS2, all right, these two material, tungsten disulfide, they have come up in a big way as possible 2D materials for the use in semiconductor. Now, semi-metal, if we write down, then basically a semi-metal is a material, as you can understand, whose electrical properties lies between a metal and a semiconductor, right? Now, the relatively smaller gap is there, right? And what are the examples? It's molybdenum ditelluride, tungsten ditelluride, and platinum diselenide. So, these are the materials which are basically 2D materials, and as you can see, these are all synthesized materials. When you bring molybdenum and telluride together, we typically have these molybdenum ditelluride materials available to us, whose conductivity lies between that of metal, pure metal, and a semiconductor or an insulator. If you look at 2D families of material, then typically they include this accents. We have these TMDs, dicolonides, right? Transition metal dicolonides are there. 2D materials, MOF. We have covalent organic frameworks and 2D polymers and perovskites and oxide. Perovskites and oxide are typically used in many of the solar applications, solar cell applications, right? So, as you can see on the right hand side, you have these graphene sheets available. You have these TMDs also available, which is transition metal dicolonides, which are available to us. And then there are many other type of material, but more importantly we are interested in graphene for a material, and TMD as also a material in 2D family. Come to challenges of 2D material. One of the challenges of 2D material is of course the scalability and production. It is difficult in scaling up the synthesis methods for high quality large area 2D materials, and that's a major bottleneck. Unlike silicon, it's very difficult here to actually scale up the whole synthesis process in a linear fashion without compromising on the output of the material itself. The defects and material quality also makes a major problem area when you try to upgrade it, because like grain boundary and vacancies and defects are there. Obviously, the third point becomes important, where the sensitivity to oxygen and moisture is there, leading to the degradation of the material itself. And till now 2D material, how they interact, or a very standard model is not available for comprehensive understanding of the material. That's the reason this challenge is there for the 2D material. The first point, which is integration with existing technology, because typically a time will come when your 2D material and CMOS technology will be sort of has to be compatible over a period of time for it to have a seamless integration. The cost and commercial viability has to be there, and which is still not there. And then there are challenges in terms of handling the 2D material itself, right? For example, one of the example is challenges with the interfaces affecting the addition, and the device performance is a major issue in a 2D material interface. Let's look at the future scope of 2D materials, where you will see this coming up in a big way for a smaller dimension. First is electronics and optoelectronics. Optoelectronics devices where you use perovskites, flexible electronics, or a major input. You have quantum computing and quantum technologies. They are used for quantum sensors and quantum information regions. Then they're also used as energy storage, for example, batteries, supercapacitors, and solar energy conversion. One area where it is coming up in a big way is basically wearable electronics and wearable devices for all medical applications. Then you have organic LEDs, for example, for stretchable electronics and for use in IoT devices. Then they are also used for sensors and detection, as I told you, is coming up in a big way. Spintronics and catalysis is also where 2D materials are used for high speed memory devices and for low power. We have already seen all these quantum computing, spintronics, sensors, energy conversion, electronics, and optoelectronics. These are the application of 2D materials. One important point where advantages of 2D material are there is known as thermal management of the 2D material. And biomedical application is also another area where 2D material has been used for quite a long time. Let's finish off this discussion with maybe a single layer as an example. Molybdenum disulfide transistor. This is a single layer molybdenum disulfide where you have chromium or gold as the gate, where you are applying a gate here, and you have the source and drain being applied. Say this is the source which is grounded, and you applied a VDS, drain to source voltage here, and there's a 2D material which is basically sort of sandwiched between these two gold contacts here. The buffer layer is silicon dioxide here, and the substrate layer is basically silicon, where you can apply a backgate bias in order to do it. The thickness of this layer is 6.5 angstrom and is deposited on a doped silicon substrate with 270 nanometer thick silicon dioxide. So this is 270 nanometer thick dioxide. This hole is 50 nanometer, out of which this is 6.5 angstrom substrate. The substrate acts as a backgate bias, and therefore you can change the threshold voltage by applying relatively small voltage at the backgate. And the monolayer is separated from the top gate by 30 nanometer hafnium oxide, hafnium dioxide, which you go. So you can have silicon dioxide also, but typically hafnium dioxide has got a higher dielectric constant, and therefore EOT is less. And it is grown by atomic layer deposition technique, which is ALD technique. And if you see the current versus the backgate voltage, as you can see, as the backgate voltage is changing, the current goes on increasing as the backgate bias becomes more and more positive, right? And current becomes larger and larger. For even a small millivolt of 10 millivolt, you get a current of approximately 350 nanoampere, which is approximately 0.35 microampere. But some 35 microampere current is flowing at VDS of approximately 10 millivolts. Right, this is an experimental data which is available to us using 2D material. Right, so you can see a large change in the current because of the single layer MOS2 layer. Now, if you see the current versus top gate characteristics, as the voltage obviously goes on increasing, the current increases. As you can see, its red line is the 10 millivolt, this is 100 millivolt, this is 500 millivolt. For a fixed backgate bias, you see the subthreshold slope comes out to be approximately 74 millivolt per decade, and and the device can be completely turned off by changing the top gate bias from -2 volt to -4 volt. So the swings are relatively small in this case in order to switch off the device dimensions very easily. Similarly, if you look at the right hand side figure for a VBG of 0 volts, this is the current versus drain voltage which you see, and almost a linear profile is available to us for positive and negative values of drain to source voltage, where you change the value of VTG by 4 volts minus 1.5. This is the gate voltage which you put. So when you put more and more negative gate voltage, the current actually starts to drop down because you don't have large number of carriers available for you to participate in the current formation process. For VDS equals to 10 millivolts, the ion to IOF ratio is 10 to the power 6, whereas when you take it to 500 millivolts, the ion to IOF ratio increases to 10 to the power 8, which is a 2-order increase in the ion to IOF ratio when you change the VDS value from 10 millivolts to 500 millivolts. And of course, the subthreshold swing is 74 millivolt per decade at T equals to 300 Kelvin. So by this study, I just wanted to show to you experimentally that research papers are available where already good amount of research has been done on replacing silicon by 2D materials, and then also showing how to change the backgate, front gate biases and materials in order to achieve the best option or the best performance in this device. You can also do a nucleating ultra thin dielectric layer. That's a major concern which is there, that rather than the active layer, can we concentrate on silicon dioxide. One of the method is that enables a 5 nanometer, which is 50 angstrom high K dielectrics for top gate 2D FET. So if you have if the top gate can be actually as small as 15 angstrom or even lower than that. So for top gated FET with high K films as thin as 3.5 nanometer, will give you very low leakage, right? And that's one of the major ideas which you will get for nucleating dielectric thickness. Typically of the order of 3 to 4 nanometer hafnium dioxide can be used. Big advancement going on in 2D FETs. How to use 2D FETs? Obviously reduced channel dimensions, and typically 0.34 nanometer thickness of graphene has been used for the shortest possible gate length. And these are the various methods by which you can actually do both channel engineering and gate engineering for advanced in 2D FET technology. And you can do, for example, you can do a vertical channel, then you can do a stack formation, you can do vertical channel here, you can do stack formation, then you can do shadow evaporation and form the channel. And these are the various complementary FETs: gate all around FET, CNT FET, fin gate, gate all around, and so on and so forth. So these are, I just wanted to give you an idea about where we are moving in next 1 decade or so, and where we will be actually concentrating possibly in the materials aspect when it goes to a 2D FET. So let me recapitulate what we learned for this lecture. We gave you an idea about 2D material, 2D FET, properties of 2D material, various types of forces which are responsible for the materials, 2D materials. How can you manipulate 2D materials, what are the techniques available, synthesis techniques available. As a case study, we discussed 2D FET device where the active area is replaced by 2D materials, and we saw that it gives me a result which is almost close to your standard silicon device. Further, we can manipulate the 2D material in order to get a fin based device, in order to take a MOSFET, shallow trench isolation based device, and so on and so forth. So this work is an ongoing process. Many of the things, many people across research groups across the world, they are working on it, and possibly we would expect to see a major paradigm shift in silicon technology, maybe post 2032, 35, possibly in that domain. So with this, I thank you all for your patient hearing. Since this is my last class, so I hope you enjoyed going through all the modules. As far as I was concerned, I thoroughly enjoyed the whole process, and I hope that you will learn something from this course which will help you for your future, as well as future understanding, as well as growing from basics of the devices till a 2D material. The whole range has been tried to covered in this lecture. Obviously, as you will move ahead, you will also see TAs and myself coming and helping you out in terms of your assignments and understanding. So feel free to drop me email if you have any queries related to the course, and you want any materials related to the course. Feel free to drop an email to me, and I will surely reply. And I again wish you happy learning for this course, and all the best for examinations if you are appearing in any of the examinations here. All the best, and thank you for your patient hearing.